Hello everyone, this is Dr. Liu. 2 years ago, I made this YouTube video showing a robot simulator developed by Python, VTK, and wxPython, which also support OPC UA communication protocol. It can work as an OPC UA client or an OPC UA server. Some YouTuber ask if I can make a tutorial. I couldn't do so until recently. So I'm going to make a series of tutorial showing how I did this, and hopefully you like it and find it is useful to you. Let's get started. So this will be the first video of the series. It is a comprehensive one. The content will cover objective, development tools, why I choose Python, VTK, and wxPython. And I will briefly explain the OPC UA standard and its information model, and also how to build the robot information model. I use some tools, and also how I got the robot joints 3D STL model. Then I will explain the simulator system architecture, its application GUI, and some test environment that I prepared to run this simulator, and showing you some running examples which I actually already showed in the previous video. Last but not least is future study, which I would like to share some of my idea, and hopefully someone else can extend or explore more from there. So my goal is to develop a robot simulator, a simplified one, and in which the 3D CD model of robot can be loaded when the simulator starts. And also I expect I can interact with the robot in a 3D visual environment, and the simulator should have an operation panel where I can manually jog the robot, display the robot position, and also run a robot program in automatic mode, just like a real robot does. And the robot simulator should be able to connected to a robot OPC UA server as a client, and synchronize robot movement with the server. It should have a built-in OPC UA server, so other OPC UA client, robot client, can connect it to. I expect the robot information model follow the OPC UA specification and save in an XML file, which can be loaded when the simulator starts. There's several aspects to consider when we select the development tools. Language, robot model display environment, software GUI, OPC UA support, multi-threading support. Why do we need multi-threading? Think about, the simulator will have two windows, one to display the robot movement, another window for operation interaction. So if we put everything into one thread, most likely you will experience very slow response when the robot is in the movement. Same thing will happen if the OPC UA communication happen at the same time when the robot is in the movement. So the multi-threading actually is very critical. I learned this when I run into the implementation later. So among those choice, I selected the Python because it's a high-level language and very easy to program, has a lot of package support. For the robot visualization and interaction, I choose the VTK, which is pretty good 3D computer graphics programming tools or library. It is a wrapper of the low-level OpenGL API. A lot of information can be found from a VTK organization website. For the software GUI, I choose wxPython. It's a wrapper of the cross-platform GUI API for Python programming. Initially, I chose the Ticket, which really gave me a lot of trouble, even though it is bundled with Python, but it has a lot of obsolete support. Eventually, so I switched to the wxPython. For the OPC UA support, the free OPC UA, it's a very good package, very easy to use. Obviously, you need to have very good understanding about the OPC UA, which I'm going to explain briefly in the following slides. So the usage itself is straightforward. More information can be found from this link. So Python supports multi-threading by adding the threading package. It's straightforward. Once we use multi-threading, another package called a pub sub package will be needed. That is very useful to send a message from one thread to another thread. So it's very good tool to use. So the robot simulator will have built-in OPC UA client and server capability, which can use OPC UA protocol to communicate with other systems. So what is OPC UA? These slides will show you a brief explanation. First of all, OPC UA is a new standard for data communication in industry automation. It's defined by OPC Foundation. A lot of people may be familiar with the classic OPC, which is based on the Microsoft COM technology, which provide the OPC specification, OPC DA, OPC HDA, OPC A and E. With the latest advance in the computer technology, like object-oriented programming, XML, web service, service-oriented architecture, and so on, OPC is defined to cover not only the well-proved classic OPC functionality, but also to expand data support beyond the simple hierarchical organization of items in the classic OPC specification, and also to apply the usage into even a wider range of industry application with more complex data like a DCS system, MES, or ERP. There's a lot of information can be found from OPC Foundation website, so we're not going to talk a little more here. If you look at this figure, beside the core OPC standard, you can see that OPC has two fundamental components, very important. One is transport mechanism, the other is data modeling. The transport mechanism defines different way for different use case. It is defined as a service in abstract, and it's basically can be specify a technologic mapping for implementation later. So it's independent from the existing proprietary solution. It's open for future, and the specified mapping technology mapping basically address three tasks. Data encoding. It's for internet communication, you will go with UA binary. For the internet communication, you may go with XML. Also secure the communication, and also how to transport in the data. It can be UA TCP method or SOAP over HTTP as a web service. So the data modeling defines the rule and the basic blocks necessary to expose an information model of device, control system, or any other complex system. OPC UA basically borrows the object-oriented concept from the computer science. It allows us to define the information model as a network of nodes with various type of reference. So with this approach, we can define very complex data structure. OPC UA standard already define several core models that can be applied in many applications. Other organization or industry association, they are building their specific models on top of OPC UA base. And the OPC UA also defines the necessary access mechanism to retrieve the information model. So OPC UA itself covers a lot, but we don't need to implement it from scratch. To support the compatibility, OPC Foundation has provided a set of OPC UA implementation. It is a communication level, there's many stacks available, and they also provide the software development toolkit. At application level, there's a lot of sample codes and the test tools available. So free OPC UA is a Python package that is developed by Python, which is based on the OPC UA communication stack. We will use it in this development. So on top of the base OPC UA information model, we can define and extend domain-specific information model for device, controller, machinery, and or MES ERP system. Many organizations have been working on domain-specific OPC UA companion specification, such as automation ML, PLC Open, AutoID, ISA 95. VDMA as the most famous Europe Machine Tool Industry Association. They work with OPC Foundation, has released OPC UA companion specification for machine tool, as well as robotics. So the first version of the OPC UA companion specification for robot is released in 2018. It defines the robot information model with robot object type, variable type, data type, and reference types. So in this study, I didn't use that complex model. Instead, I just referred to it and defined a simplified robot OPC UA information model, just like this right figure shows. I use a free UA model software called UMX, downloaded from Beyond website, to define a new OPC UA object type called a robot type. That is my simplified OPC UA information model for robot. Underneath, we define the joint variables, robot operation mode, alarm event, and some other variables. Then instantiate a robot type object called the robot1 from that, and finally compile this robot information model and export it as XML file. To make it compatible with free OPC UA package, I made some modification over this XML to make it simple. Alright, so after we build the OPC UA information model for robot, now it is time to prepare the robot CD model for the simulator. we can download this 569 robot from this website. It's a free website. You can find this robot and download it as STP format. Meanwhile, I search the website, the Google website, and find the robot specification datasheet from this website. It is very important to have this information. It tells us, what is the rotation direction of each joint, what is the limitation of each joint, and also most important, what is offset between each joint. For example, the offset XYZ offset between joint J2 to J1, J3 to J2, etc. So after we got this model, I used CAD software. It's a free CAD software called a FreeCAD. We can use any other CAD software like a Creo or SolidWorks to dismantle the robot model and save each joint as individual STL files. Something we need to pay attention is we need to translate the coordination orange of each STL model to its geometry center. Otherwise, the original model, after you dismantle from the initial STP file, it's in a very different location. If you use that model to assemble it in the robot simulator, you couldn't find where that component is. Very difficult to assembling. So it is important to load each STL model of the joint into the CAD software, translate or modify their coordinate origin to a proper location where is the best location for the joint rotation, and save them as a new STL file, which will be used for the robot simulator to load. So when the robot simulator starts, it will load the joint STL model one by one, and it will also use offset data extracted from the robot specification to arrange the proper location of each joint to assemble the whole robot into the VTK environment. And after that, the simulator will load the OPC UA information model of the robot in XML file. It will use the variable, the property definition to construct the robot object, and use that for the later OPC UA communication. Okay, we finally come to the cool stuff. So this will be the developed robot simulator GUI. It has a mainframe, visualization environment, which is a VTK panel, operation panel, and status bar. In this VTK panel, it will display the robot model. We can change the view, we can zoom in, zoom out, we can move the robot around. Not physically, just move the robot view around. Operation panel will be used to control the robot manually and automatically. So it has two operation mode as a drop-down list: manual mode, auto mode. In the manual mode, we can use those sliders to manually jog each robot joint independently, and so here we'll display each joint's minimum limit and the maximum limit. The go home button, whenever you click it, robot will move to each joint will move to its 0 position. The axis on off button will basically either display or hide those each joint coordinate. That is just it's kind of like auxiliary, to help display. and that's an auto program. If the robot is in auto mode, we can either click this one, select a program, or just use default robot program, which is text file. It's just a make-up robot program showing for each joint, which angle we intend to go. It's very simple. So once the robot program is selected, if we click cycle start, the robot will move each joint to the commanded joint in the program. And if you want to stop, you can click cycle stop. So basically the program can have a loop or just has one cycle. So here is I want to remind, at the very beginning I mentioned why I choose the multi-threading package is because assuming if I put the VTK display and also operation panel into one thread, and if the robot is running the program in cycle, pretty much we have no chance to click the cycle stop button because the whole resource is occupied by the robot movement in the VTK environment. So make the visualization and the operation panel as a separate thread, make the system much more user-friendly. Anytime we can click cycle stop, it will send the message to the display environment. It will stop the robot movement. If you click cycle start, it will start again, and the operation will be very smooth. So that's the reason we need a multi-thread. So another button, OPC UA URL, which is used if we want to connect this one to a OPC UA server. And here is the OPC UA server address. So assuming there's another OPC UA robot server is running, it could be another this robot simulator or a TwinCat PLC developed robot simulator, which I'm going to explain later. We can connect it to, and here's the button, click it, it will connect it to this OPC UA server. And then if the robot in the server, OPC UA server is running, this robot will synchronize with that as a client. And in addition, as we said, this robot simulator can work as a server, OPC UA server as well, which is this button. So once we click this button, this simulator will become OPC UA server. It will use a robot OPC UA information model in the XML file. And at the same time, this OPC UA server's endpoint is this address. So another OPC UA client can connect to this server use this endpoint, and then whenever this robot is running, the client robot will basically follow or synchronize with its action. It's cool. So another button is reset. It's for review purpose. Whenever you click reset, basically the view of the robot display will go back to its original position. The exit will exit the application. It will pop up message just to confirm we don't want to accidentally quit the application. The operation log is used to display what is the action robot is doing. For example, cycle start, cycle stop, OPC UA connection, we connected to a OPC UA server, successful or failure, and stopped, and we started the simulator as a OPC UA server, or we stopped. All the kind of operation log will be displayed over here. clear log means become more, you want to remove it, you can click here. So to test the OPC UA communication, I prepared another robot simulation environment in Visual Components, which is a commercial software for automation, modeling, and simulation. So I import the previous downloaded FANUC 60IB robot model into this VC environment and save it as a VC model. Then build this robot model in this VC environment. Then I can manipulate the robot joint in this environment. The VC environment is very good for robot simulation and display, but it can only work as an OPC UA client. By using its plug-in OPC UA protocol and also the TwinCAD back of TwinCAD PLC, we can develop extension to this VC environment and make it as an OPC UA server. So this OPC UA server will disclose the robot joint position as OPC UA information model. So from here, I'm going to show a few running examples. First one is use the robot simulator as OPC UA client and use VC environment with TwinCAD PLC extension as OPC UA server. So whenever the VC environment robot is in motion, the robot simulator client will synchronize with it. So as we can see that in this environment that the VC environment is running and the TwinCAD PLC expose all the joints data, and those data are basically synchronized to this OPC UA client. So the second example shows two OPC UA clients connected to the same OPC UA server that we set up before. So as we can see, the two robot simulator basically synchronize the motion with the server. So the last example shows two robot simulator, one as OPC UA server, another one as OPC UA client. So the left OPC UA server needed to disclose its OPC UA address to the right side client. The client needed to utilize this address connected to. And after that connection is established, the no matter the OPC UA server is in auto mode or manual mode, the robot movement in the server will be synchronized by the. So one potential future study is to develop an OPC UA information model bridge. Assume we have a physics automation production line. We want to have build its digital twin, equivalent digital twin, and you want the digital twin and the physical system to seamlessly communicate or exchange data. In order to do that, you need to have comprehensive information model of the production line available. So in this OPC UA information bridge, we should have an information model extractor which can extract the physics automation components, CD information, kinematic information, dynamic information, and on another side, the OPC UA server will be able to link the digital twin and the physical automation product line together. And meanwhile, it can provide data to other applications through either OPC UA or other communication protocol. Alright, so this will be end of the this tutorial. Thank you very much for your interest, and you can find the original YouTube video from this link. Hopefully you like this video and find it is useful, and feel free to leave comments or give me any suggestion. I can improve further. Thank you.